So welcome to the third part of lecture 2, which is about the general stochastic epidemic model. So in the last part, we looked at deterministic modeling when the population was large, which is a reasonable approximation if for certain questions we want to study the general large population behavior. However, in small populations, stochasticity plays an important role, for example, for extinction, as we could see from Tom's analysis. So the first model we looked at, the Reed-Frost model, and the models we will look at in this section are all so-called stochastic epidemic models. And here are some references where you can look a little bit more about those type of models. However, it quickly also becomes clear that these type of models rely heavily on stochastic process theory, which is not something we will expect you to know a lot about while taking this course. So we more or less give this here as an appetizer because it underlines the importance of looking at stochastic phenomena. But again, for many cases, it can be okay to take a deterministic approach, but in particular settings, this is not sufficient. And of course, also the stochasticity is closer to real nature, as we do expect things not to be able to replicate itself in the exact same way because it's based on chance phenomena. So looking at one particular model, the general stochastic SIR model, so general stochastic epidemic model, can also be described not as we only showed in the deterministic model, but it can also be used as a continuous time Markov process description. So again, we divide the population into categories of susceptible, infectious, and recovered, and look at a continuous time description, but the state of what we are looking at, namely the number of susceptible and namely the number of infected or infective persons. There's no distinction in this model. These are going to be integer numbers. So it's this number of susceptible can be 0, 1, 2, 3, 4, and so on. And also the number of infectious can be 0, 1, 2, 3, 4. Opposite to the deterministic SIR model with continuous state, where we saw that we can use any real value between 0 and the total maximum number of susceptibles to describe this. And of course, why is there a distinction? Well, the big distinction is once one of these quantities, namely and in particular the number of infections, turns 0, this epidemic is over because you would have this multiplication by I part. Of course, also the same for the number of susceptible, but that was clear also in the other. But here, the number of infectious, once this starts to become 0, the epidemic is over. And of course, within a deterministic ODE type description, this is not possible. So it will just become very low, but it will never really become 0. So this is one way to describe this. If you say we are at a current state, it's S of t, I of t, and we're going to determine when will something change. And the first question is how can this actually change? So there are two types of changes. One is that there's an infection. An infection means there will be one less susceptible afterwards and one more infectious afterwards. So that's the one type of transition we can have. And that happens, and we will say this happens at a particular rate. And this is the same quantities we have just from before. It's our transmission or contact rate parameter times the number of susceptible times the number of infectious. You can derive this easily by saying that any individuals has a contact with a particular other individual at the rate beta, and then you can say, what is it, how many of my contacts will be with infectious individual? Well, that'd be the I of t times beta, and finally, how many of the susceptibles are there? Then this is all multiplied by S of t. And the other transition we have is S of that we go that we have a removal of one infective, that it moves to the recovered class. So that's ST remains the same and IT goes one down. And the rate at which this will happen is gamma times IFT. Again, RFT is again implicitly given because we assume a fixed proportion. And now we are taking the integer structure of the population into account. Once I of t is 0, this epidemic is over. So you can also have extinction in this model. To describe this formally, this can be done within the context of so-called stochastic processes. And you have so-called piecewise constant rates, which are described here. And actually this here describes that you say that your length of how long you are infective is an exponentially distributed random variable. We will look at in the next slide on how to simulate such a model, but it's just important to know that this is something which can be handled within the context of stochastic processes. So here's one example where we say the population consists of 100 individuals which are initially susceptible, one additional initial infective individual, and then to the transmission and the gamma parameter are given as follows. And now we simulate 10 trajectories of this general epidemic model. As you can see, these epidemics can vary quite a lot. So this is the number of susceptible. It starts with 100 and always goes down, and the question is how far it goes down. It can tell us something about the final size. But you see, you have this very different type of epidemics just because chance plays a role here. So how do we simulate something like that? Well, we can look at such a model, like we can describe it here now. We say, okay, so what's the maximum time interval, maximum time we want to go to? Beta and gamma are the parameters we know. Initial number of susceptible, initial number of infectious. Then we say, okay, x and y initially are equal to n and m. We say there are two types of transition which can occur, namely there's a susceptible becomes infectious and an infectious recovers. And then we have here our bookkeeping. We say we have a data frame which we initially start with all the information we have, and then we continuously build up the data frame. This is not really a fast simulation, but it's a simulation which will work for our purposes. And the nice thing here is that this type of algorithm is actually very common. Also, you can use this for a large system, but it has a problem also with speed, which you would talk about in some other class. But here we will just look at the simple form of something which is called the Gillespie algorithm to simulate such a dynamic system. So we said we have rates for each of the two events. So we will see which of the two events will happen. One of them has the rate beta times S times I, and the other one has gamma times I. So these will be the two rates that we will have. So this is the first one is S to I, has rate beta times X times Y, and this is the other one is gamma times Y. So what we will do is we will simulate two instances of the exponential distribution. One is from this distribution here, and one is from the other distribution. So this is simply how long do we have to wait for either this event or the other event. And of course, which of the two occurs first is the one which has the minimum time. So we will ask which, so this will be a vector of length 2. We can also look at that in our simulation. So I'll have to change the simulation like this. And change to the corresponding R file. And here's the function which we will be using. So let's say we have t, just take some random time, and beta, just to stay something 1, and gamma 0.2, n is equal to 100, m I'll put 1, and initiate, we will have these event levels here, these two, and here's our initial more or less empty data frame. And now we will loop until we have not passed the maximum time, and while they are still infectious individuals. So of course this is the case in the beginning. We can also check that. Now we will simulate two waiting times, first event and second event. So this is the first event. Sorry. Which is the waiting time for the first, and this is the waiting time for the second. So of course the first one is with the one which occurs first, and the other one is not going to occur thus. So we will take that I is the minimum of those two. Of course, that's the index 1. And then we will say, okay, this was the time we had to wait for this event to occur. So we will have to update time. So time is not 0 anymore, but now t is, in this case here, exactly equal to the timing. And then we have to look at which of the two events it is. If it is an S to I event, which was will be the case, of course, because it was the first one, then we will update one less susceptible, one more infectious, and so on. So this will be our function, and then we'll simply build up our return data frame row by row by row. So this will not be super fast, but it will do for what we will have to do. And we can look at here, this is the plot, which this is another version of the plot that we showed with these values. Of course, you can also think about that. You want to say, okay, so how does this relate to the deterministic model that we were showing? And Tom had a plot on his slides like this. So I'm just going to extend this a little and say I'm not just going to take 10, I'm going to take 250 simulations here and just do the same plot that I had before. So here's the plot with the 10, but the plot with the 10, but now with the 250 shown. And what is interesting here is I plot the deterministic curve. Maybe I should put this like this, and I'll do the same again, just so it will be a bit bigger. It's easier to see. So here I use also the alpha channel as part of the plotting for the color. You see that up here, you see that I use color. I use 0, 0, 0, that's black, and then I use here the alpha channel because otherwise it would simply be black around here. So more or less you can think of this, that you put colors on top of each other. The darker the color is, the more of the trajectories are located in the neighborhood. And you see here, this is this would be the solution of the SIR model when you describe it as a deterministic ODE type model, right? And we said early on that there is a connection, that this is when the population is large, the mean of the simulations at a particular time point will converge to the deterministic model. But you can see here, it's not easy to see, but you can see that it appears to be a bit off at this stage. But of course, you can also try to do this a bit more. So we can say, okay, we can take, instead that we're not taking the population of 100, let's take a population of 500. It will take a bit longer to run, but we can try to have a look at how it looks then. And of course, you also note the variance of this, which can be, of course, very, very large. And this is sort of the idea of that you use stochastic epidemic models. There is some kind of variation still running. As you can see, once you have a population of 500, 250 trajectories, that's not super fast anymore. And of course, if you have now a population of 10 million, which might be the thing which you have if you want to model something for Sweden, then of course these type of models, individual based, or at least simulation based, are not that feasible anymore, and you need to think about better algorithms. So here you now see the case for 250 trajectories for 500 individuals. You see, of course, here the mean curve, and as we said, like the larger the population get, the closer this deterministic ODE model is to the mean curve. But you see that there is some discrepancy between the mean curve, which we say here the ODE model, and the stochastic model. So that's which is part of the variation. Okay, so let me return to the slides. So this is one way of how we can simulate such models. And this is just to say we also have these type of models in our toolbox. They are stochastic. They're probably in some sense closer to reality. But the important question is also, how can we in this case do inference? And that's the problem when things become quite complicated. I just here have the exercise which you're supposed to look at. I'm supposed to talk about this here. So if you want to do inference for such type of model, things quickly become sort of like not so nice anymore, but that's where a lot of the research is also ongoing. So I put here the star, the asterisks, to indicate this is not material we will really expect you to know as part of this course here, because it's simply too complicated. I just want to give it as an outline. If you're not interested, it's fine to stop here. So this is just to tell you that what we have is observation of the stochastic process over a certain time interval, and we say tau is the duration of the epidemic, at least that's when it stopped. We have some infectious contacts. We have observation on that, T1 to Tk, and then we know for each individual how long it was, also how long they were infectious, so that we will assume a particular distribution for, let's say they are exponentially distributed, because they that would correspond to the rate we simulated earlier, where the rate of the exponential distribution used for this would be gamma. And then if you have full observation of the infectious contacts and the how long they were infectious, then you can do that you have a product here over the how long they were infectious. So this is just the individual the continuous the density function for each of the exponential distribution, and then you have this part here, which is covering how long it took them before they got infected. And of course, here the complicated part is that here this lambda of u is a piecewise step function depending on how many currently infected and how many are currently susceptible. And one complication of this is that you have to do an integral here, but of course this I and S, they change as step functions, so this is going to be a sum, so that's a bit easier. But one problem will be, of course, that you probably will never have access to the times when they actually got infected. You usually don't know that, so that's one of the things which are difficult to do in this case. And the other thing is that this assumes here that you have observations in continuous time, but typically you will never have, at least on a larger scale, never have continuous time. You will have some kind of resolution, like maybe day, or in some cases we will even have only weekly data. So there exists approximation how to deal with this if you have time series data. So you discretize this type of systems and say, okay, how many new cases do we get in a particular interval of a width of 1? So that could be, for example, 1 day. And then you say, okay, well, the conditional probability that you escape infection during this interval is approximately equal to this quantity here, where lambda of t corresponds to typically would corresponds to I beta times I of t. And then you say that this new number of infection, it will be a binomial distributed random variable, and the probability to escape infection, right? So this is, for example, something which is very closely to the Reed-Frost model that you have, and you assume here that this is a constant probability, and your time interval, if it's small enough, then this will be a good approximation. And then you can do generalized linear model part, which I don't want to go into for this lecture, but it's possible to actually put some of this into either a binomial regression with a log link, not the ordinary logit link, but a log link, or you can use a Poisson regression with identity link to model all of this. But that goes beyond the part of this course, so this is here for those who are interested in stuff like that. I'm going to stop here with the third part of the lecture, and on Tuesday I look forward to receive some of your questions about all of these 3 lectures. And please note that the 3 exercises which you're supposed to look at, and I will use a small breakout room session so you can discuss a bit with your fellow students. So with that, looking forward to see you in the live session. I hope you enjoyed the lectures, and if not, or if so, please provide feedback in one way or the other. Okay, that's it, and I'm going to end the meeting now.